Hello everyone, this is Scott from the Vapor team up here at NCAR, and this is a demonstration on how to use Vapor. Today I'll be working with a data set that is a very large data set. It's about 15 gigabytes per time step, and it comes from a model, a flavor of WRF called WRF-LES. Um, for those who don't know, Vapor is a cross-platform, open source, free to use desktop application to visualize mostly meteorological data, but we also span into ocean science, space science, and many other fields of physics. But this demonstration will be focusing on a high-resolution WRF-LES model that came from Adam Wise from UC Berkeley. So thank you, Adam, for letting us use your data. The first thing I'm going to do, though, is convert my WRF data into VDC. And like I said earlier, this is a large data set. And what can tend to happen with large data sets is that the uh, responsiveness of Vapor can slow down depending on how much data you're passing onto your GPU. And so what the VDC does is it allows you to look at your data at different levels of compression. And then once you think you've kind of got a ballpark feeling on how you want your visualization to turn out, then you can crank the or turn off the compression and render it in its original form, and kick off your visualization. But for exploratory purposes, VDC is going to help us in this regard. So I'll do that first, and then I'm going to try to create a visualization similar to what we see here. Now, Vapor is comprised of a set of renderers. There's about 10 in total, and what we're looking at right here are four renderers that we call the image renderer. Here at the bottom, we can see this base map, and just kind of showing the terrain and satellite imagery, as well as the model renderer is another one, which we have pointing at these wind turbines. And the model renderer basically can take any STL file you have and embed it into your scene. After that, I'm going to go into the flow renderer, which shows these streamlines that basically are just lines that follow the wind vector at a single time step. And then finally, I'll wrap it up with a simple volume rendering that we see back here behind the wind turbines. So with all that being said, let's jump into the first step, which is creating a VDC, a Vapor Data Collection. So again, the link to download Vapor is below, and once you've downloaded and installed Vapor, you're going to get a set of tools, and I've installed it on my Mac, and there's all these data conversion tools as well as Vapor itself. So Vapor is one of the applications that comes bundled in the installer. But right now, I'm going to convert my data to VDC by first, it's a two-step process. The first step is creating a metadata file with one of these tools that we call the VDC creators. You can see here we have WRF VDC create. There is plain old VDC create. If you're dealing with like raw binary data, you can use that to define your metadata file. And let's see, I think the other big one is CF VDC create. So if your data is CF compliant and that's CDF data, this does basically the same thing. So the first thing I'm going to do, and just a forewarning, I'm not going to convert Adam's data because it's so big and it takes a while depending on the size of your data. So I'm going to just do this on some sample data. So it's really, I should stop babbling and just do it. Let's do WRF VDC create. And then I'm going to point it to data WRF, and then I have some Hurricane Katrina simulations from WRF. I'm going to point at one of those files, and let's see, 29 or 13, sure. And I'm just going to call this test.vdc, and test.vdc will be my Vapor metadata file. So kick that off, and there we go. If I do an ls for my current directory, here we have test.vdc has been created, and this of course will be written to whatever directory you're currently in, but for demonstration purposes, I'm just piling it into my current directory. The second step is just throwing the number 2 and making the same command. So I put number 2 into, there's the VDC creation phase, and then there's the actual algorithm that we run on the data. And the actual algorithm is called WRF to VDC in this case. But again, you can see CF to VDC, etc. So just fire off the same kind of command with the same order of arguments. And at that point, I have my newly formatted data that I can look at different levels of compression, as well as my VDC. So once I've done that with my data, I can open Vapor. I've already installed it, and I have it in my startup bar down here. I'll click Vapor, and I'm going to load my VDC, which I've already converted before this presentation. But let's see, open VDC, and then I'll go to my Atom-Wise directory. Okay, so I'm going to go to my Atom-Wise directory where I have my VDC, click Open, and here we go. First things first. Atom's domain seems to be a pencil. This is the 5th nested domain in his simulation, and so the largest domain probably spans CONUS, the United States, but this is the most resolved one. The first thing I'm going to do, though, is there's an adjustment to Vapor I need to make, because if you can tell right here, when I mouse click, I can rotate the scene, but the scene is being rotated about a point in the middle of the domain. And Atom is mostly interested in things happening down at the bottom at the surface. And so to better be able to navigate, you can see it's like the domain is being swung around on a pendulum when I focus at the bottom like this. So one thing that will make the navigability of Vapor a little easier is if I go to my navigation tab, go to my viewpoint tab, and then instead of my origin being at the middle, which is roughly 10,000 around here where I'm showing with my mouse, I'm going to set the origin on the z-axis to 0. And so my new origin of my scene is going to be right down here, and it's going to be much easier for me to move around if my origin is co-located with what I'm trying to focus on. So with that being said, let's move on to our renderers. So I'm going to go to my renderers tab up here on the left, and I'm going to start with an image renderer. This is basically the base map that we saw in that picture that I had in my slides. So I've clicked on New, created a new image renderer from the list of renderers. And the first thing I'm going to do is, I can go ahead and enable this one, but it's not going to show much because Vapor comes with geo-referenced images that often are very easy to just apply to your data. But since this is an LES simulation, it's very high resolution. It's very focused on one region in Portugal. So Atom created a custom image file. So I'm going to load that custom image file in the Appearance tab. And instead of the default natural Earth image, I'm going to select the satellite imagery that he generated. And I'm going to unclick georeference because it's not a geotiff. But he custom made this image of Portugal. And the other thing I'm going to do in my image renderer is apply a height variable in the variables tab. So I will go to my variable selection and select HGT. And it looks like it's a little bit off right now. So one thing I can also do is go to my geometry tab, and I can I want to translate it. So I want to translate this by -1000. Let's see how that looks. How about 3,500? I want to push it down. That's a little bit too far. How about 4,000? Whoops, wrong way. -3,200. Let's see how that 32, 31. Yeah, let's go with 3100. So we're scaling it. We're pushing it down on the z-axis. We're translating it by negative 3100 meters. And like I said earlier, we converted our data into VDC. And so by default, we're looking at this with very low fidelity. You can kind of see if I zoom in, it's very blocky with our color map variable. So this is a relatively inexpensive renderer. I'm going to crank up the fidelity to high. And now we see the true reconstruction of our height variable in Portugal, Portugal. So that's the first step, my image renderer. Next thing I want to do is click on New, and then go to my model renderer. And here we have a wind turbine. I'm going to do exactly that. So I'll click on OK. And the trick to my model renderer is first to select this model/scene file. So I'm going to select Adam's STL file. He's got two of them. And so he's got a tower, and then this one, NREL 5 megawatt small, is the turbine. So I'll start with the turbine. Open that up, and then I'll enable my renderer by clicking on this checkbox. And it's not quite easy to see, but I'm going to cheat, guys, because one of the things with the model renderer is you have to know what kind of coordinate system is embedded into the STL file. And I'm going to cheat right now because I already know how to position it with these translation tools. So knowing this ahead of time, I'm going to type 613 into my X, 47434 70 into my Y translation, and then my Z will be translated 450 meters. And there we have, I don't know if you guys can see that, but there's our turbine floating on the top of this hill. The next thing I'm going to do is load in the tower, and to do that, I'm going to click on this duplicate button. I can duplicate this renderer on this visualizer, and it will apply all the same settings to a new renderer, except what I'm going to change is the model file. So I'll select the tower, and then I'll turn it on, and there is our wind turbine. Whoop, looks like we got a little hiccup there. That's interesting. It looks like it's a little bit too high. Let's see if I can drop it down to 350, and then I'll click on the renderer for the turbine, and I'll make that 350 as well. Okay, that looks a little bit closer to the ground, I suppose. All right, so now that we have our wind turbine, the next renderer that I'm going to create is the flow renderer. So again, I'll click on New, Flow, and the flow renderer is probably our flagship renderer in Vapor. This is probably one of the most useful tools that's in the application. What I would like to do is put some streamlines vertically in this region that I'm circling with my mouse. And to apply seeds, we call them seeds, which are basically the origin point of a streamline or a path line. And to constrain where we put those, I can go to my seeding tab, and I will enable the region mode in Vapor, which lets you select where you're rendering to or where you're putting seeds. To do that, I will click on the region drop-down menu up here at the top, and then I'm going to zoom way out because by default the region mode encompasses the entire domain. But I'm going to shrink it down at the top with a right mouse click on these little boxes, and I'm going to just make a tower of seeds. So let's see if I zoom in further. Okay, and I want to left mouse click to transpose this box. So this is where I will be distributing my flow lines, about right there. In my seeding tab over here on the left, what I'm going to do is I'm going to set my z-axis seeds to something like, let's say 16 on the z-axis, and on x and y, I'm just going to do 1 by 1. And that's going to give me a column of seeds 16 high, right there. The first thing we see are these big fat lines, and they don't look 3D. So to fix that, I can go to the Appearance tab, enable 3D geometry, so they look more like tubes. And then I'm going to decrease the radius scaler to make them much thinner. Another thing I can do is go to my Variables tab, and I want to pick a color map variable of W, my vertical wind velocity. Go back to the Appearance tab, and I can adjust the transfer function to give it a a better color map, which is a very subjective term, but you don't want your colors to be too washed out, otherwise you can't see differences in your variable values. So let's see, I'm going to go back to my seeding tab. I'm going to nudge this a little bit like that so we can see what the winds are doing above the wind turbine. Something like that. If we want to go down to the surface, we can do that. Okay, anyways, that's a brief demo of the flow renderer, and gosh, I'll go into more videos, I presume, in the future with the flow renderer. But meanwhile, I'm going to disable my region mode, and I will finally make a new volume renderer. So again, I'll click on New, Volume, and this renderer is kind of expensive. So over here we can see in our data fidelity controls we are at low fidelity, which is a good thing, especially for a demonstration. I'm going to scroll down to my renderer table down here, and I'm just going to let's just turn it on. Let's see. Okay, so the first thing we see is this giant red block, and the volume renderer basically works by the user applying two parameters. I guess there's the color parameter being applied to the data field, and there's also the opacity parameter. So I'm going to mess with those right now to give us a more compelling visualization. First thing I'll do is pick W, the vertical wind component. Then I'll go to my Appearance tab. And whenever you have a distribution, like a modal distribution, like a witch hat, it's usually best in your transfer function to highlight the tails of it. And so this is my PDF of W. Low values or negative values are in blue, high values are in red. And what we want to do is mask out most of the values so we can see through the volume. And so what I can do is click on the transfer function and drag this bar down. And then we've masked out all of the values between these 2 points. They are not being shown. Only the values at the tails of the distribution are. And those values at the tails are increasing in opacity as they get more extreme. So that's a simple first approach. So now we can see, gosh, I don't know if I've translated my image properly. But this is the field, the variable field for W in our simulation. One thing that I would like to do lastly is go to my Variables tab, and let's see how long it takes to render a high resolution image. Gosh, a little over 30 seconds. And you can tell when I just move the scene, vapor becomes, there's a lag between when you move the scene and when you get a response. So this is kind of an example of why you would want to use VDC to explore your data and then crank up the resolution for your final visualization. So those are the basic principles. I know this is a rough cut at a visualization, but it does demonstrate the principles behind Vapor. So as always, please like and subscribe if this was informative to you. And please, I'll put a link to our Discord forum. If anyone has any questions or needs help with Vapor, our team is here to support you guys. So thanks for watching and hope to see you again in a future Vapor